Have you ever wondered how the universe looked before the first stars were born, and how their formation changed the cosmos? These are some of the questions that the James Webb Space Telescope will try to answer. NASA's JWST is about to take us on a journey back in time to witness the birth of the first stars and galaxies in the universe. This remarkable mission will allow us to witness the cosmic dawn, a time period that has remained a mystery to us until now. In this exciting episode, we will delve into the fascinating mission of the James Webb Space Telescope and explore what we can expect to discover about the early universe and the first stars that sparked the beginning of time. Finding the first stars. According to scientific theories, the first stars in the universe emerged from the primal gas that filled the cosmos after the Big Bang. This gas was predominantly comprised of hydrogen, helium, and small traces of lithium and other light elements. Initially, the gas was cold and dense, but as the universe expanded, it started thinning out and heating up. Eventually, some regions of the gas became denser and underwent gravitational collapse, leading to the birth of the first stars. These stars were unlike any stars we observe in the present universe. They were massive, ranging from tens to hundreds of times the mass of the Sun. Moreover, they were extraordinarily bright, emitting thousands of times more light than the Sun. They had a brief lifespan of just a few million years before exploding into supernovae or collapsing into black holes. The emergence of these stars significantly impacted the evolution of the universe as a whole. The first stars produced elements like carbon, oxygen, and iron, which enriched the intergalactic medium. As a result, they enabled the formation of planets and life. These stars also ionized the surrounding gas, creating bubbles of hot plasma that merged and reionized the entire universe. This made it transparent to light and allowed the formation of the first galaxies. Over time, these galaxies grew and merged to form large-scale structures that we can observe today. To study these first stars, scientists used the JWST, designed to observe their infrared light. Detecting the first stars in the universe is challenging as they are far from us. Their light has been shifted from the visible and ultraviolet to the infrared range, making it difficult for traditional telescopes to capture their signatures. To overcome this, the scientific community has developed various techniques and methods to detect the presence of the first stars. These include analyzing the spectra of galaxies to identify the presence of particular elements, examining the emission line's intensity and shape, and observing brightness fluctuations. Another method involves measuring the amount of helium in the spectra of galaxies, which is done by studying the peaks of light at specific wavelengths that correspond to the energy levels of helium. Using these advanced techniques, researchers can gain valuable insights into the early universe and its evolution over time. How important is it to study early stars? The quest to locate and study the first stars in the universe is a complex and exciting challenge for scientists. Studying these ancient celestial objects can reveal much information about our universe's early history and development. It also presents an opportunity to test and refine existing theoretical models and simulations of the first stars and their formation processes. By observing the first stars through James Webb, we can better understand their properties, including their mass, luminosity, temperature, and lifetime. This information can provide valuable insights into how the first stars differed from those later and how they influenced their surrounding environment. For example, the mass of the first stars can help us determine the amount of energy and radiation they emitted, while their lifespan can reveal when they gave birth to the first supernovas and black holes. The luminosity of the first stars can provide insight into how bright they were and how they influenced the intergalactic gas by ionizing and heating it. Additionally, the temperature of the first stars can help us understand what elements they synthesized and how they enriched the intergalactic medium. Ultimately, studying the first stars holds tremendous potential for advancing our understanding of the universe and our place within it. The number distribution and diversity of the first stars can provide valuable insights into their prevalence and variation in different regions and times of the universe. For instance, the number of first stars can help us understand how many formed and to what extent they contributed to the ionization and chemical enrichment of the universe. The distribution of the first stars can reveal where and when they were formed and how they clustered and correlated with the density and temperature of the primordial gas. The diversity of the first stars can help us understand how they differed in their properties and behaviors, and how they were affected by the initial conditions of the primordial gas and the feedback effects. Further, we can explore their relationship with subsequent generations of stars and galaxies, which can provide insights into how the first stars influenced and shaped the later evolution and structure of the universe and their connection to the observable objects we see today. Imagine a universe where the connection between the first and later stars could determine how energy, radiation, and elements were transferred. This connection could have even affected the formation and evolution of the stars, and if that wasn't enough, the link between the first stars and the galaxies could have triggered and facilitated the growth of the first galaxies, determining their properties and shapes. Sounds fascinating, doesn't it? But the fun doesn't stop there. The connection between the first stars and observable objects can help us trace and identify the first stars by examining the light and signals they emitted or left behind. We can compare and contrast these objects with the ones we see today to understand the evolution of the universe over time. Thanks to the help of Webb, we can test and refine our theoretical models and simulations of the first stars and their formation processes. We can even experiment with the effects of dark matter, cooling feedback, and metallicity on forming the first stars. This can lead to discoveries and new questions, and can inspire the development of new models and simulations. Isn't it amazing how much we can learn about the universe through the connection between the first stars and everything that came after? We can use this information to compare and contrast the data obtained from the first stars with that of the later stars and galaxies. This will help us understand their similarities and differences and how they are connected or separated. Additionally, by combining the data from the first stars with information collected from other sources and wavelengths, we can synthesize and integrate them to better understand the early universe. This will help us to determine how they complement or contradict each other and how they form a complete and coherent picture of the early universe's challenges and limitations. Technical challenges and scientific opportunities. The James Webb Telescope is a state-of-the-art scientific instrument with great promise in searching for the universe's first stars. However, this search has its significant challenges and limitations. One of the primary hurdles that James Webb must overcome is the contamination of its infrared light signals by many other sources. Although the light from the first stars is expected to be in the infrared spectrum, it's not the only infrared light present in the vast expanse of space. Many other sources of infrared light, such as interstellar and intergalactic dust and gas, stars, galaxies, and even the zodiacal light from the solar system, can interfere with or obscure the detection of the first stars. This interference can create noise and confusion in the observations and make it harder to isolate and identify the signal of the first stars. To overcome this challenge, James Webb must rely on various techniques and methods such as filtering, masking, subtracting, and modeling. These methods will help reduce and eliminate contamination from the other infrared light sources, allowing the telescope to focus on the signal from the first stars. However, the calibration and interpretation of the data collected by James Webb are complex processes. The data will be affected by many factors and uncertainties, including the performance and sensitivity of the instrument, the observation time and strategy, the data processing and analysis, and the theoretical assumptions and models. These factors and uncertainties can introduce errors and biases in the data, making it difficult to calibrate and interpret. Therefore, James Webb must use various techniques and methods to improve and validate the data, such as cross-checking, correcting, testing, and comparing. By doing so, James Webb will be able to unlock the secrets of the universe's earliest stars and expand our knowledge of the cosmos. Let us share some exciting insights into the challenges and possibilities that lie ahead in the search for the first stars. There's no doubt that James Webb has a big task ahead of it, and there are some limitations and hurdles that it may face. However, with the help of advanced technologies like machine learning, artificial intelligence, and quantum computing, we can overcome these obstacles and achieve groundbreaking results. To supplement James Webb's mission, we can leverage other telescopes and wavelengths such as radio, optical, and X-ray telescopes and combine different data types such as images, spectra, and signals. With these powerful tools and technologies, we can refine our search for the first stars and discover new wonders of the universe. This will open up new avenues and opportunities for the search and study of the first stars, including discovering new and unexpected phenomena, generating new and intriguing questions, and inspiring new and innovative ideas. We hope you enjoyed exploring the fascinating world of astronomy, astrophysics, and cosmology with us. Thank you for joining us on this exciting adventure, and we can't wait to have you with us for more thrilling cosmic discoveries.